Okay. All right, so 14, who wants to,
I got it.
all right, stop talking, please. Listen, Marlena's got it. 14.
Ethanolic acid has a stronger particle attraction.
Good. Ethanoic acid has stronger particle attractions. Good. Very good. Good answer. What's another way to say that? Stronger forces of attraction. Right, good. So ethanoic acid has stronger forces of attraction. Remember, on table H here, it has a higher boiling point. Right? So it's over here. That means it takes more energy to boil. Okay. 15. First part. What has to happen for a liquid to evaporate? Remember when I had everybody holding hands? Remember?
The surface. Yeah.
We all turned around and held hands?
Yeah.
And the surface was up front here?
Yeah.
So when the surface evaporated, what did they have to do?
They
They had to let go, right? You weren't holding hands anymore. So go ahead, Kieran, and answer the first part there.
Of 15?
Yeah, in order for a liquid to evaporate, it has to.
Reach its boiling point.
You know that's not right.
Got
Because water can evaporate and not boil.
True.
So, you were starting to say it.
Let go, man.
Good, just let go. Explain that in chemistry terms here.
I think I know that. Forces of attraction.
Must be.
Broken.
Very good. Yes, at the surface, the liquid particles must break free of their forces. That was the whole point of holding hands, shaking hands, whatever. So you got surface particles here. If they're going to evaporate, they are being attracted to the particles below them. They have to break free of those particles so they can get out. So the answer to the first part is the liquid particles must break the forces of attraction to evaporate, but only at the surface. Remember, it can only evaporate at the surface. That's actually probably the most important question on here, is what we just said there. So it has to break forces to evaporate. Okay, how is evaporating a cooling process? Who wants this one? Go ahead.
It takes heat.
Right, what takes it?
The particle.
There's two, the vapor or the liquid?
The vapor.
Right, so when it evaporates, it takes the heat with the vapor particles, leaving the liquid cooler. When I was boiling the water in the vacuum chamber, it actually started getting colder and colder. I think it was Kieran who was reading the temperature. So it kept losing energy because of that concept there. Okay, good. All right, so finish that up for Friday and put that away. Let's talk about the one behind me. I'm going to actually close this because it's, bless you, a little bit weird how bright it is.
No.
It's like blinding me. Every day I think of that song. All right, that's supposed to be a bonus on that quiz. You guys got to remind me, I'll forget. All right, who knows the answer? What is it?
What were the layers again?
Oh, blinded by the light. Okay, number 10. Who knows the answer?
7.
Nick knows. He says 4. Why, Nick?
Because CL2 has
Hey, hold on before you answer that. Can I use magnets to help us here?
absolutely.
All right, would you say Cl2 looks like this?
Yep.
Two of these together? So what would NO look like?
It's just one of those.
Just one of these?
Different color.
So this would be NO?
Yeah.
You sure?
No.
What is NO? What element is NO?
It's two.
Ah, so now I'm helping him out here. So, and everybody else, trust me, Nick, not just you. So NO maybe looks like this? Okay, so would we say, based on the board here, that Cl2 and NO in terms of how they look are kind of the same? Yes, they have different atoms, but they look kind of the same as far as the shape. Okay, good. Okay, so why is it 4? So it's not 4 now. I hope you realize that. He said 4, rightfully so, so he actually had a good answer because in his head, he thought that's what NO looked like. So he was thinking, if NO has half the particles, I need twice as much of it. That was what you were thinking. That's good. That's really good logic. But I fixed it there, help him reframe the question. They both basically have 2 atoms. So they're both the same sized molecule. So, you want me to keep picking on you or go to someone else? I can move on. All right. Anka?
Pick on me.
Because it's an H3, there are 4 molecules total, so the 4 molecules would be the same, so 2 different
Good logic, but also not number one.
2.
It's 2. Got it.
Here's what I want to try and stress to you, and this is why I'm reviewing this question. The number of atoms in the molecule doesn't affect the volume. So I know that sounds crazy to you because like one person takes up less space than 4 people. In chemistry, molecules are so small it doesn't really matter. So if you have 2 atoms, or if they're all together in one, the amount of space they take up themselves doesn't really matter. Because in a gas, it's not about the size of the molecule in that volume, it's how much space the whole sample takes up. So hopefully that makes a little sense. But the logic is right. I mean, it's the same concept as what he was saying. So it's not 1, it's not 4.
3. 2.
Try 2.
It's 2. Now let me explain this in an easy way. So if I have 2 containers that are both 2 liters, 2.0 liters here, 2.0 liters here. Okay, imagine they're basically the same. They should be the same size. If I have, what do we got? Cl2 in here and CH4 in here, 2 liters is 2 liters. Sprite, Pepsi, Coke, 7-Up, think of other sodas, Mountain Dew. If I have 2 liters of Pepsi, I have 2 liters of Coke. Do I have more of one or the other? No, I have the exact same amount. So in chemistry with this type of question, and we did talk about this in the past, but I really wanted to show you a Regents question pertaining to the concept. If you have the same temp, pressure, and volume, so the same size container at the same pressure and temp, everything about those 2 particles are the same, including the number of particles. So the number of particles in here equal the number of particles in here. Why? Because it's 2 liters versus 2 liters. The analogy of soda, I'm trying to help you there. So if you have 2 liters of one soda, 2 liters of another, you have the exact same amount of both. Same amount of soda particles. That sounds weird, but so you have the same amount of particles. Why? Because the volume is the same. Has nothing to do with the formula. They're trying to confuse you with that. Okay, that's why I'm going over this question. Next Tuesday, there's one similar to this. What is STP? Standard temp pressure. If you don't know what those numbers are, and it's not important if you know the numbers or not for this question, but they're right here, table A. So it's not about knowing the numbers. It's about understanding same temp, same pressure, same volume, same number of particles. Okay? Same number of particles. So hopefully that makes some sense, that the volume needs to be the same, and then the molecules are the same. All right, so we're going to move on here. The homework due today, we're going to go over second. First thing, we got to go over yesterday's homework. We never did that. Take out yesterday's homework. Too much to do these days, so we're behind.
I don't remember what it was.
So just don't give us homework.
It was the worksheet that was due Monday and Tuesday. So 1 through 14 was due yesterday. Due Monday. And then 20 through 49, that was due yesterday. So that's the one I'm going with. 20, all the surface problems. So everybody should have this. Does anyone need a copy? Did you lose it? Want to make sure you follow? You don't have this one at all? Oh yeah, I'll get it to you. Yeah. Okay. So here we go. What is meant by an elastic collision? Oh, I don't know. Alexis, what do you think? Number 20. What'd you put for that?
There's no loss of energy.
Good, there's no loss of energy. Very good. So in the universe, when particles collide, what do they do with their energy? Transfer. But overall, the energy stays the same. There's no loss or gain for the entire universe. It's just transferred. So that's elastic. So the total energy stays the same. Good. 25. Relationship between absolute temp and kinetic energy. Caroline, what do you think? Sorry. Say it again. Yeah, temperature measures the average kinetic energy of a substance, but this is saying what is the relationship between temperature, and when it says absolute temp, it means Kelvin. So what's the relationship between Kelvin and kinetic energy? And when I say relationship, do you know what I mean?
Relationship.
How they're related, good. I'm thinking of a graph. So if this is the temperature in Kelvin, and this is kinetic energy, what does that graph look like? It's a direct relationship. Very good. As temp goes up, particles gain energy and move faster. So that's the answer to 25. Good. 29. What's significant about absolute zero? Annika. All movement stops. Good. So 0 Kelvin. Right. I told you guys the bad joke, didn't I? Yeah, yesterday. Didn't I say it yesterday?
It's okay.
Or 2 days? Yeah, he's okay. 30. Who knows the answer there? What's the factor? What's the factor that the kinetic energy increases if it goes from 300 to 900? 3. Yeah. 300 times 3 is 900. So if the temperature goes up from 300 to 900, that means right here, kinetic energy does the same. So a factor of 3. Before I forget, I have candy up here.
You give that kind of candy?
Not this. This is for AP Chem Lab.
I would eat all of those.
Jeez, I was like, wow.
Well, like one of these? No way.
Yeah, I'm
No
like,
way.
wow,
We have little nerds here and Laffy Taffy, which is an awful candy my wife's bought it. I don't know. So, it's against my morals here to hand that out, but it's left over. So if you want some after class, come up and get some. 33. Compare evaporation of a contained versus uncontained. So if you look up here, okay, I have a liquid contained, tops on. If I open it up, now it's uncontained. Charlie, what's the difference?
A contained liquid, the liquid will evaporate and then it'll like go back into the liquid.
If it's contained?
Yeah.
Good.
And then if it's not, the liquid will evaporate and expand out from the container.
Good, right. So if I left the top off, would the liquid in here, the water eventually evaporate completely, nothing left?
Yeah.
Yes. But if we put the top on, she said it will go back into the water. What did we learn? What's that called?
Dynamic equilibrium.
Dynamic equilibrium, right. Up and down, right? Evaporation, condensation, because what builds up in here? Vapor pressure, right. Okay, 34. I just explained it. Okay, so vapor pressure. All right, Autumn, this is your key. Your cue, I should say. Vapor builds up. What's it do? Collides, right. So vapor builds up. It collides with themselves in the walls in here, and it builds up and goes back in, and that's called dynamic equilibrium, when it evaporates and condenses at the same speed. 35, sorry. Explain why increasing temp increases the rate of evaporation. Amber, what do you think? Why when we heat up a liquid, it evaporates faster? Good, so if we heat it up, kinetic energy increases, good. But I'm not going to let you off the hook that easy.
Aww.
So yes, kinetic energy increases, but why does that mean it evaporates easier or faster?